Welcome back. Today we're looking at smart pointers, types that behave like pointers but carry extra capabilities beyond a plain reference. If you've used unique pointer or shared pointer in C++, these will feel familiar. Rust has a whole family of smart pointers in its standard library, each one solving a different problem. Box gives you simple heap allocation. Rc gives you shared ownership through reference counting. RefCell lets you mutate a value through an immutable reference in a controlled way. Each one trades off a different property, performance, flexibility, where checks happen. And together, they let you build data structures that would be awkward or impossible with plain references. They're also how Rust lets you safely express patterns that are common in other languages, recursive data structures, graphs with shared nodes, types with interior state. By the end of this lesson, you'll know when to reach for each and how to combine them in the canonical patterns that real Rust code uses every day. Let's start with the simplest one. Box is the simplest smart pointer. Write box of T and Rust allocates a T on the heap, handing you a pointer to it. When the box goes out of scope, the value is automatically dropped. The heap memory is freed. Box has three main uses. First, when a value is too big to live comfortably on the stack, very large structs, for instance, that would blow out stack frames. Second, when you need to own a value whose size isn't known at compile time. This shows up most often with recursive types, like a linked list where each node points to another node. Without box, the compiler would refuse to compile the type because it can't figure out how big each node is. Box has a known fixed size, just a pointer, so it breaks the recursion. And third, when you want to store a trait object, the way we saw in Lesson 11 with box of din shape. Accessing the inner value feels just like accessing the value directly, because box implements the Deref trait, which we'll see in a moment. For most of the time you'll interact with a box, you won't even notice it's there. The Deref trait is what makes smart pointers feel like real pointers rather than wrapper objects. When you call a method or access a field on a box, Rust automatically dereferences it to the inner value. You almost never have to write a star manually. In the example, we have a box holding a string. We can call .len on it directly. The method call goes through the box's Deref implementation, fetching a reference to the underlying string and then calling len on that. From your perspective, the box is invisible. This is called Deref coercion, and it's how a box of string can be passed to a function expecting an ampersand star. Rust follows the chain of Deref implementations automatically. Box of string derefs to ampersand string, which derefs to ampersand star, and Rust threads all of that together when you make a function call. You can implement deref on your own types to get the same treatment, though for most application code, the smart pointers in the standard library already do it for you. Deref is a small but pervasive piece of what makes Rust's smart pointers feel ergonomic. The drop trait lets you customize what happens when a value goes out of scope. Implement the drop method, and Rust calls it automatically exactly once when the value is destroyed. This is Rust's version of a destructor, and it's how every smart pointer in the standard library does its cleanup. Box frees heap memory. Rc decrements its count and possibly frees if it hits 0. Mutex guard unlocks its lock. File closes its handle. You rarely implement drop yourself in application code. But every time a box disappears, every time a file goes out of scope, every time a lock releases, drop is what made it happen. The pattern is called resource acquisition is initialization, or RE, a concept borrowed from C++. Acquire resources when a value is constructed, release them when it's dropped. Because drop is automatic and deterministic in Rust, unlike, say, Java's finalizers, which may never run, you can rely on it for critical cleanup like releasing locks, flushing buffers, or rolling back transactions. Drop is one of Rust's quietly powerful features. Sometimes, a single value genuinely needs to have multiple owners, a node in a graph, a shared configuration, a value that many parts of your program read from. Rust's ownership rules normally insist on a single owner, so this feels like a contradiction, and in some sense it is. The solution is to wrap the value in a smart pointer that manages multiple owners. For single-threaded scenarios, Rust gives you RC, short for reference counted. Wrapping a value in RC new gives you a shared handle. Calling RC clone on that handle creates a new owner. It doesn't deep copy the data, it just increments a counter. The value stays alive as long as at least one owner exists. When the last RC is dropped, the counter hits 0 and the underlying data is freed. In the example, we create an RC holding a vec and then create 2 more handles with RC clone. Strong count shows how many owners exist. This is cheap and clean, but RC is single-threaded by design. If you need shared ownership across threads, you'll use its thread-safe cousin arc, which we'll meet in the concurrency lesson. RC by itself also doesn't give you mutation through the shared handle. For that, we need one more piece. Normally, Rust's borrow rules are checked at compile time, but sometimes you know your code is safe in a way the compiler can't see. You want to mutate a value that's accessed through an immutable reference, because the larger structure is set up carefully enough that no one else is touching it right now. RefCell lets you do this, with the borrow rules enforced at runtime instead of compile time. You call borrow for an immutable reference, or borrow mut for a mutable one. RefCell keeps track of how many borrows are active and panics if you violate the rule. One mutable or many immutable, never both. This is called interior mutability because the type appears immutable from the outside but permits mutation through its interior. It's a deliberate escape hatch from Rust's default rules, and it's used sparingly. Good uses: mocking objects in tests, caches where readers also invalidate, graph-like data structures where cycles naturally exist. Bad uses: wanting to mutate a value and reaching for RefCell instead of just making a variable mutable. Use it when you need to, but prefer ordinary references when you can. Rule of thumb: if you can't explain why you need RefCell in one sentence, you probably shouldn't use it. Here's the canonical pattern you'll see in Rust code. RC wrapping RefCell. The outer RC lets multiple parts of your program share ownership of the same value. The inner RefCell lets each of those owners mutate the underlying value, with the borrow rules enforced at runtime. Together, they give you the flexibility of a shared, mutable value, familiar from other languages where everything is shared and mutable by default, while keeping everything inside the safe, documented boundary of smart pointers. In the example, we create an RC of RefCell of integer, clone the RC a couple of times, and each clone mutates the underlying value. At the end, we read the final value through the original handle. This pattern isn't automatic. You give up some compile time safety and some performance. But when you genuinely do need shared mutation for a graph with back edges or a parent-child relationship, this pattern is the right tool. For multi-threaded contexts, the analog is arc of mutex of T, which we'll see next lesson. That's smart pointers, box, Deref, drop, RC, RefCell, and the combinations that build on them. One final lesson to go: concurrency, where everything we've learned so far really pays off. See you there.